Hi guys, it's a guy Olumde, and today we are gonna be considering a very crucial data structure, which is the tree data structure. A tree is a hierarchical data structure composed of nodes where each node connects to one or more child node. So why we call it an hierarchical data structure is because it is structured. It is structured in such a way that we have the root node, we have the children node, we have the parent node, the child node. So it is hierarchical, meaning that in it, just like a tree having branches, we see that branches that are at the top will be much higher than branches at the bottom. So it's just hierarchical, like the branches of a tree. So whereby there are nodes that actually represents a parent node to one or more child node, right? So that's what we are trying to see here, whereby a tree is a hierarchical data structure that is composed of nodes. So these are the nodes. So where each node actually connects to one or more child nodes. We can see that this particular node here connects to this child node here. So and each node in the tree contains the data it stores and reference to its child nodes, right? We see that each of these nodes will contain a particular value, which is the data it stores, and the reference to the other node child nodes. So the most common type of tree is a binary tree in which each node connects up to two child, a left and a right child. So this is a typical binary tree. So it's just a common type of tree. So in which each node will connect to up to two children. What we mean by that is that each node will actually connect to up to two children, a left child and a right child. Just like in this case, whereby this root node, we can call it the root node because it's the only node that does not have a parent. So it is the root node here. So and this node connects to two children, left and right, the node on left and the node on right, which corresponds to the left node and the right node respectively. So and that's it about a binary tree. So it's not going a binary tree in a binary tree, a node is not going to have more than two children. So that's how you see that it connects to up to two children. Here is the implementation of the tree node class. So because we do represent it as a class, so when we are giving a structure like this, so in order to implement it in code, we represent this structure as a class. So and the class is the tree node class. So in the initialization, we'll be passing in value to the particular class object that we are trying to create, and then when you pass in the value, so it's gonna create a node. Don't forget, this is a node class, a tree node. So it's gonna set the value attributes to the node objects, and then the left attribute and the right attribute. So this is for a typical binary tree, so that has a left and a right, or let me say that have up to a left and a right. Cause for a binary tree, it might not have both. It might only have left node, it might only have right node, it might have both left and right, it might not have both left and right. But one thing about binary tree is that it will connect to up to two children, so it cannot connect to more than two children, either two or less than two children. So this is how we're going to be implementing the class. We just pass in the value, and then the left and the right attributes will be added subsequently. We are going to create it as attributes to that particular class object. So now let's consider certain terminology now that is used to address a tree. We have the parent node, is a node with one or more children. So this is what we call a parent node. Any node that have one or more children is a parent node. So as you can see, this node 1 have node 2 and node 3 as children, right? So child actually is a node that has a parent. So we see that both node 2 and node 3 in this case are actually child to node 1, so they are child nodes. Similarly, subtree is actually a tree that is formed by a node and its descendants. So it's just like saying sub-array, right? So it's like we have a tree. Now let's consider this one tree that is more longer. So this particular tree here, a subtree is actually a node, and it's constituted of a node and its descendants. So you can see that this particular node 2 this particular node 2 here is a subtree because it consists of it's actually comprised of a node and it has descendants. So similarly, this node 5 is also can be a subtree of this whole tree. When we say subtree, it's a subtree of the whole tree. So because it has a node and it has some descendants, which means child nodes. So that's what we call the subtree. Now a path is a single continuous sequence of node that is connected by edges. A single continuous sequence of node. So it's just like a path along the tree. So a branch of the tree, that's what we call a path. So look at this path now from node 2 to node 6. Look, that is shaded. That shaded region from node 2 down to node 4 to node 5 to node 6. So any sequence of node connected by an edge can be a path. So now depth now corresponds to the number of edge from the root to a given node. Number of edges from the root to a given node. So if you have to find visually now, you are just asked to determine the node of the depth of this node 5 in this particular tree. Look at the node 5 that I'm talking about here, right? To find the depth, you just have to count the number of edges. When we say edges means that line. This is edges here. So look at edges here. This is edges. It's just the line that connects a node to another node. So the number of edges between the root node to that particular node is the depth of that node. So look here now, because this is the root node, so its depth is 0. No node connect the root node to the root node. It's actually the root node, so its depth is 0. But when we go to determine the the depth of this node 5 here, the depth is 1 because an edge, just one edge, is between the root node and node 5. But if we're talking about node 7 now, the depth is 2 because from the root node down to node 7 there's two edges, so in between them. So the number of edges from the root to a given node is what make up the depth of a node in a tree, right? Now let's talk about the attribute of a tree now. The roots. Root is an attribute of a tree, so and it is the topmost node of the tree and the only node without a parent. So look, for instance, this is the roots of this tree. The roots of, when you say attribute of a tree, is actually a term that we use directly on the tree, right? Like now saying that roots of the tree is an attribute of the tree, right? And it actually corresponds to the topmost node of the tree and the only node that does not have a parent. It is the only node without a parent. It is the root node, and it is the topmost node of a tree. Also, let's talk about the intermediate node, which is a node with a parent node and at least a child node. So that is it. Intermediate, it's in the middle. So these two nodes here, node 2 and node 5, are both intermediate node because they has a parent node. A node cannot have more than one parent, right? No, it can't have more than one. It can only have a parent, but it can have multiple children. So, and for a binary tree, it can have up to 2 children. So, considering this intermediate node, node 2 and node 5, you see that they have a parent and they have at least 1 children each. So, you see that node 2 have even 2 children. Node 1 and node 7. Node 5 also have 2 children. Node 6 and node 7. Alright. The leaf is actually a node with no children, so we call it leaf because it is at the edge, let me say at the end. So it is a node that does not have children. Look at node 1 here, node 7, node 6, node 7 here. They are all leaf node because they do not have child node. So edge now is the connection between two nodes, like I said the other time. So it is the connection between two nodes. So it's the line that joins two nodes together. Why the height is the length of the longest path from the root to a leaf. The length of the longest path from the root to a leaf. So when we say height, it's also an attribute of the tree because a tree will only have an height, so it doesn't have multiple height. And what height means is that the length of the longest paths from the root to a node. So considering this now, the height is 3 because if we look at the longest path that we can ever achieve from the root to a node, it will be from the root to a leaf node, such as 6 now. and then if you look at the length, is just 1, 2, 3. Length is determined by counting the number of nodes. So this is the height of this tree is is 3, because the length of the longest path that we can ever see from the node to any given node is 3. So similarly for this one now is also 3. So 4, 5, 6 or 4, 5, 7 or 4, 2, 1 or 4, 2, 7, they are all the same, and they all have the same height of 3. So these are the common terminologies and attributes of a tree. Now, how is tree traversed? Tree traversals. When we are traversing an array, we just have to index, traverse through from one index to another index till we get to the end of the array. For tree now, we have two major way of traversing the tree. We have the depth first / DFS method, and we have the breadth first / BFS method. So the depth first search, just like the name implies, depth first, is a method that is used for exploring all nodes of a tree by starting at the root and moving as far down a branch as possible before backtracking to explore other branches, right? What this one is trying to say is that is a way of navigating and traversing a tree by starting at the roots and moving as far down. So instead of just moving haphazardly, it actually will move far down into the roots, to the height of the tree. It's gonna move far down, meaning that it's gonna move from here and follow this path downward and follow this path downward, and it will make sure that it gets to the leaf of the tree before backtracking. Now that it has gotten to this first leaf, it's gonna backtrack because there's no more node again to move downward again. So it's gonna backtrack again back to this place, and when backtrack to this node 2, it then go on to the right node of node 2 to explore it, and going on to the right node is gonna go deep down until you get to the leaf, which is node 3. Actually, had it been node 3 extend, probably node 3 have a left node and right node, just like node 5 and node 2. It's gonna keep going down. That's what depth first means. It's gonna go in depth. So, and after reaching this leaf node, it's gonna backtrack again to node 2, and then it's gonna backtrack again because node 2 has been explored. We just explored node 1 and node 3 from node 2, so we're gonna backtrack to node 4, and then it's now gonna go on to the right node, which is node 5. So instead of having to navigate the tree in such a way that it's gonna start from the root node, then go to node 2, then go to node 5, then go to node 1, node 3, node 6, node 7. It's not gonna do it that way. It wants to go through in depth to the very depth of the tree, and then backtrack again to go and attend to the others. So that's what the DFS means. So DFS actually is implemented recursively. So it's implemented recursively, and what that means is that it recursively calls itself, going deep down, and this is how the code looks like. So this is the DFS function that taking a node, so which is the root node, right? This node that is passed to the DFS function is gonna be the root node as first. So, and then if node is none, it's gonna return. What this is trying to say is that if node is none, that is imagine for this root node now, for this leaf node here, let's consider this leaf node. For this leaf node now, according to the definition we talk about, so its left and right will be none. Its left will be none, its right will be none. Why I say that is because the root node does not have a left and right attribute, so they are gonna be null by default. So what this place is trying to say is that if the node is none, then return. Don't go on, don't loop again, stop the loop and return at that point. That's what this place is trying to say. So otherwise, if it is not none, that is if it's something like node 2 that have a left and right node, or node 5 that have a left and right node, or node 4 that have a left and right node, so what we now do is that I want to process this particular node, be it node 2, we want to do something with it based on our own logic and what we choose to do with it. And after doing it, we then call DFS. So this is where the recursion starts to work by calling this same DFS on the left node and on its right node. So that's how the depth first search method works. So it processes the current node, then recursively call DFS on the left node of that current node, and then call it on the right node. So what do you think will happen now on calling it on the left node? Left node is gonna explode itself. That's why we call it depth first, because we call it on left node first. Left node is gonna make sure that it explode everything to the left. After everything to the left has been exploded, it's now gonna backtrack again before it comes to the right node that we have here. So that's simply what the DFS does. The other one is the breadth first search. The breadth first search traverses the node of a tree level by level. It processes the node at the present level before moving on to the node at the next level or next depth level. Don't forget what I talk about depth. Depth is actually the number of edges from the root node to a given node. So considering this particular here, you see that the depth is 0. When we move here, the depth is 1. When we move here, the depth is 2. And same thing applies to this one. Depth here is 1, depth here is 2. So now BFS is very good at traversing the tree level by level. So as you can see here, it will first traverse this whole level here. Then after traversing it, it's going to traverse the next level, then the next level, which is this last level here. So unlike the depth first that is going to traverse the left, it's going to go deep down to the very leaf before backtracking again to the right, and then before backtracking to the right, and keep on doing like that, reaching the depth like that. So BFS is implemented using a queue. Actually, we typically implement it using a queue, and this is just how the function works out. We define the BFS function. It takes in the root node, right? The root node, and the same thing apply if root is non-return. So in a situation whereby we've gotten to the leaf, we've gotten to the end of the node of the tree, so whereby there's no node anymore. So I mean there's no left and right node, so it's gonna return at that point. Otherwise, it's gonna take the root and dequeue it. So what we mean by dequeue here is that it's gonna add this root node into a queue. It's gonna create a queue object and append roots with this particular root object into the queue. So and why queue here actually means that while there is something inside the queue, which of course there is for now, there's this root node in the queue. So and why queue, what you want to do is that it's gonna pop left. So it's gonna pop left just like a queue does. So it's gonna take the leftmost item in the queue and pop it out. And what that means is that it is not acting like a stack. A stack is gonna do a first in, last in, first out, right? But a queue is gonna, a queue is actually honest. It's gonna take the last in, it will retain the last in, but the first in will be the first out, right? While the last in will be the last out. So that's how a queue works. So that's how I'm using pop left. So just like in an array, the leftmost item is the one that was appended first. So it's gonna pop out the leftmost one, that is the one that has been there right from time. So the first in is gonna be pop out, and we are gonna collect that node. We are gonna process the node, do anything we want to do, apply our logic to it, and after that, it's gonna check if this node have a left attribute. It's gonna append it into the queue. It's gonna check if it have a right attribute. It's gonna append it into the queue, and then the while loop will just continue on and on as much as there are nodes in the queue. So it will get to a point whereby there is no more node in the queue, and by that time we would have processed all the node in the tree. So this is simply, you can see that BFS is some kind of a gentleman or a gentle lady, So, but they all have their own applications and usage. But you see, in most cases, any problem that can be solved using DFS, the depth first, can also be solved using BFS, and any problem that can be solved using BFS can similarly, in most cases, be solved using DFS. But sometimes we try to, most likely we try to use the depth first, because it do justice to most of this problem easily. So okay, now below now, we're going to be considering the differences and similarities between the DFS and the BFS. And N, actually you'll be seeing NON. N actually means the number of nodes in the tree, I mean the total number of nodes in the tree, and H means the height of the tree. don't forget what height means. Height of the tree actually corresponds to the longest path from the roots to any node. So it actually just literally mean the height of the tree. Look at this case now, the height will be 3. So it's just like the longest path or the longest number of consecutive nodes that are connected by edges. So that's the height. So right now for DFS, the time complexity is on. It takes on time because when we perform the depth first search method, it will actually search through each node, so it takes on time. Similarly, BFS will take on time because both of them are actually search method for searching the tree. I mean, they're gonna search through every node in the tree, so both of them will take on time, where n is the number of nodes in the tree. For the space now, DFS is gonna take OH space, where OH and where H represent the height of the tree. And what this means is that DFS depends on recursion. So I can say recursion. So we use a stack. Don't forget function. Whenever function is calling a function, so one will be added to the stack until the other one implements instance. So that stack now will be what we actually be using a space like this. The stack is gonna be taking up a space of OH, where H denotes the height of the tree. So what I'm practically saying is that consider this particular tree now. Imagine we are using DFS to traverse it, and we have been traversing now. We know that the stack is gonna first pop this particular node 4 in. Then because it's a depth first, it's gonna recursively call the left and the right, and it's gonna pop, it's gonna add 2 again to the stack and call left and the right, and it's gonna add 1 again to the stack. So so you see that the length, the stack is taking up 3 nodes. That means OH. So in the worst case, the stack is gonna take in OH, where H denotes the maximum length, or let me say maximum number of nodes that are connected together by an edge. So that's what the stack does. So the stack is actually taking up space of OH, where H is the height of the tree or number of nodes that are the longest parts, the longest number of nodes that are connected by edge in the tree. So that will specify the height. So another, while for BFS we take in ON. BFS should take in ON, not OH. So ON, because that's in the worst case. So now let's explain it. We'll explain both of them. DFS visits each node, resulting in an ON time complexity, right? We know that because it's gonna touch all the node. For the space complexity, it is determined by the maximum depth of the recursive call stack, and can be as deep as the height of the tree. So because the call stack is gonna be, is gonna be keeping each recursive call to the left node and the right node. So because of that, it's gonna be as deep as the height. So in the worst case, the height of the tree is n. So that's in the worst case scenario, the height will be n, whereby all the O node is on the same part of the tree, so they are not distributed. So that's it. So in a balanced tree now, whereby the height is very much minimized, it will be log n, which is much better. But in a situation whereby the height is so biased and is so biased to the left or to the right, it's gonna be ON. So similarly for BFS now, BFS visits each node, resulting in an ON time complexity as well, and the space complexity is determined by the maximum number of nodes that is stored in the queue at any time. Don't forget that for the BFS now, we said we are gonna be storing each of these nodes into the queue. Well, you'll be seeing it in the subsequent videos that I will be solving some problems. So if it's a BFS, if we're gonna be using a BFS technique, you'll see that we'll be storing, because BFS traverse the tree level by level. So the queue at any point in time will be holding the node in a particular level. Like now, it's gonna hold node 4 now, and then it's gonna hold node 2 and node 5. Then it's gonna hold node 1, 3, 6, and 7. So and that's why the space complexity for this BFS is determined by the maximum number of nodes stored in the queue at any time. So, and in the worst case, the queue can store the entire bottom level of the tree, which could contain around n/2 nodes. So that's just what you need to know about DFS and BFS. Now let's consider a real world example of the usage. The tree is actually using file system. So just like we know that file2 and directories actually look like they have a tree structure, so tree is very much useful in designing the file system. So in many operating systems, the file system is organized as a hierarchical tree structure. So the root directory is the root of the tree, right? And every file or folder in the system is a node. So the root directory. So the root directory is like the root of the tree, while every file and folder is like a node in the system. So folder can have subfolder or file as child node. That's what it means. And this structure allows for efficient organization, navigation, and retrieval of files. So when you browse through folders on your computer, you are essentially navigating a tree structure. So that's one real life application of the tree data structure. So you won't want to miss this interesting yet very very crucial data structure. So it has hundreds of questions under it that is always asked. So by top tech companies, and is even used in solving practical problems. Like now in social media platforms, they utilize trees to represent node, connections, followers, friends. So they are used they implement trees to do that. So I'll be expecting you to watch my next video that I'll be posting. So do well to follow up, do well to subscribe now so you won't miss any of these videos. Many more are still coming and you don't want to miss it. Alright, like, comment and subscribe. Thank you.